So we'll start with 1.1, which is a rehashing of what Joachim did in 30 seconds at the beginning, but a little bit more slower. So we're solving the first problem in any finite element course, Laplacian equal to a given source with some boundary conditions. So here we have the domain set to the unit square, and the bottom and right parts of the boundary have Dirichlet conditions, essential boundary conditions, and on the remaining parts you have Neumann boundary conditions. Here's a quick rundown of steps to the solution, typical workflow in NGSolve. You first import everything from NGSolve, or import what you like. If you already know the package well and you know what to import, you just import what you need. And then after that, you generate a mesh. And you can draw the mesh and query the mesh for the number of vertices and number of elements. You can draw the mesh here, and the web GUI will show you a picture of the mesh. And as you've seen in Joachim's Whetting the Appetite, you can move things around, examine it closely. If you can zoom in and you can open the controls, and there's more stuff here. And if you're frustrated by the fact that the controls are kind of looking too small, you go to full screen, and then you have more space to look around in the controls. Right? You can adjust things. Okay. That's the mesh. Now, how do we solve the problem? We declare a finite element space. Everyone who's taken a finite element course knows what this thing is, H1, and we're not equipped to talk about what H1 is at this point, but we'll just use what is called H1 in NGSolve, which is the Lagrange finite element space of the input order together with boundary conditions. So you have to specify which part of the boundary should question over there, I think. Somebody needs help? No? Okay. So by this flag, Dirichlet flag, you're specifying what parts of the boundary should get the Dirichlet boundary conditions or the essential boundary conditions. And you can query the number of degrees of freedom of this finite element space, and we'll talk more about this and how the boundary conditions affect this degrees of freedom or not in later tutorials. And you can of course always type help on an object in NGSolve, and most objects now should have some documentation that comes up in the form of Python's online documentation. As you can see, the finite element space has a lot of functions, and you get information, member functions and data attributes, and you get information on all of that here. Okay, to solve the problem using this finite element space, you declare a trial function and a test function from that finite element space. So this is the finite element space we created, and these are methods of the finite element space. They give you trial and test functions, and the difference between trial function and test function and a grid function is that a grid function has memory to store a solution, whereas a trial function and a test function are just symbolic objects that you use to declare a problem or a bilinear form. Okay, and if you become more conversant, you don't have to write this trial function and test function laboriously. You can do fancy things like this one-liner, where you get both U and V together in the trial and test, or T and T. Nothing to do with T and T. Yeah, but okay. Here's how you declare the bilinear form. If you want to solve the Poisson problem, you saw this in Joachim's Whetting the Appetite also, we make an integral of gradient of U against gradient of V, and this is how you specify the form. Okay, and as we go further in the tutorial, you'll see that you can do these three things in one line. Okay, but you have to wait for that. Okay, and here is the right-hand side. The right-hand side is X in the PDE, and you're multiplying that with the test function and integrating. And the assemble gives you both A and F. And here's the one-liner that I I told you about. So instead of writing all of this, now you can just do gradient of u, gradient of v, star dx, and then dot assemble, and that does the whole thing. Okay, now if you want to examine the system, linear system in that we just assembled, that we can ask to print out the vectors, you can ask to print out the matrices. So these are the entries of the right hand side vector. It's a lot in there. Here is the matrix. Okay, the matrix is is printed out in a CSR format of a sparse matrix. Okay, it goes on and on forever. We don't need to see all these numbers. Okay, we need to solve the system. To solve the system, you ask the assembled matrix to do the inverse method. The inverse method essentially inverts the matrix. Okay, and once you invert the matrix, you need a place to store the inverse multiplied by the right hand side, and this is the grid function we created earlier. And we are assigning to the grid function the inverse multiplied by the right hand side, and then we are asking to draw the grid function. And here is the solution. You can see the Dirichlet boundary condition being imposed in these areas, and you can ask in more detail what precise degrees of freedom are being constrained by the Dirichlet boundary condition and so forth, and we'll delve more into that in the next tutorial. And you can certainly print the entries of the solution vector if you want to think of it as a linear algebra object. Okay, and I should also mention before we conclude this little tutorial that there are many ways to interact with NGSolve. What we're doing is via Jupyter Notebook. You can also write a simple Python script and run the Python script by itself, and then you would call the Python script using as usual. And if you want a GUI, a Netkin GUI that stands by itself without any reference to a web browser, then you run the program or run the script that you wrote using Netkin instead of Python 3. And from the Netkin GUI, you can get a Python shell. There's a button there that the solve. In the solve menu, you'll see the Python shell button. Okay, so any questions?